post everything up. It's been a busy weekend. So I'll have this posted up today. We're just going to go through. We'll get more in depth on Thursday about this stuff. Also, we'll be going through, just be talking about the different things that affect the performance of the airplane, and we'll get into the charts a little bit more on Thursday. So review that stuff this week, okay? So today we're going to talk about the atmospheric effects on performance, calculate pressure and density altitude, we'll talk about how density altitude affects performance, and other environmental factors that affect performance, discuss climb performance, and takeoff techniques and performance factors. So what is the atmosphere? It's a sea of gas around the planet. That's it. Around the planet, sorry. It's roughly made up of, it's a little over 78% nitrogen, a little over 21% oxygen, and less than 1% of all other gases. That is our atmosphere. Why use the term sea?
Just like the ocean, it's more dense at the bottom.
Okay, good. What else?
There's no like water.
Okay, what else?
Isn't like air like fluid as well?
It is a fluid. Yeah, the ocean is a fluid, the air is a fluid. So what else does that mean for us as far as the atmosphere goes? If it's a fluid like the ocean and like the seas, what else?
Currents, there's high and
Currents.
low fronts.
Yeah, good. So you have currents, like you said, density. As you go deeper, it gets more and more dense. Well, we are at the deepest point on the surface, so aren't we? As we go up, it gets less dense. All right, what is atmospheric pressure? Just kind of talked about it. It is the weight of the atmosphere on top of us. And that's what it is. It is the gravitational effect of the molecules in the air molecules. So as air pressure increases, the number of air molecules in that column of air, and you'll get used to hearing that term, column of air, because once you guys get into weather classes, you'll be talking about different columns of air and how that changes. Because as we fly, we go through different columns of air. You'll go from one column of air that is warmer to a column of air that's cooler. You have different air pressures as you fly as well. So the number of air molecules in that column increases. So the couple I threw up some info up here for you. Standard pressure is 14.7 PSI, 1013.2 millibars. The big one that we deal with is 29.92 inches of mercury. And this is, you'll also hear the 15 degrees Celsius or 59 degrees Fahrenheit. And all atmosphere equates to 1 atmosphere at sea level. But the 29.92 and 15 degrees Celsius, those are important numbers for you guys to remember, right? That is the standard datum plane. All performance calculations are based off.
The inches in mercury or millimeters in mercury?
Inches of mercury.
Inches.
All right, pressure altitude is the height above the standard datum plane. One of the rules that we use for flying is for every change, 1 inch change, it equates to about 1,000 feet. So this is how we calculate aircraft performance, like I said. So pressure altitude is standard pressure, 29.92, minus the current ambient pressure at your airport, times 1,000, and then you add that to the field elevation. So does anybody know the field elevation here at Merrill Field, besides my student?
137.
Yeah, 137 feet. So it does vary, obviously, because the airport has terrain changes on it, but the elevation they use for us is 137 feet. So if the pressure was a little bit higher, it would increase the pressure altitude for that day, and so on and so forth. So it's pretty easy to calculate, not very hard. That's a formula you guys are going to want to remember, because you're going to use that a lot on the written test. And you're also going to want to know that because you have to use it to calculate the next number. And this is the most important number. It's density altitude. So density altitude is pressure altitude corrected for non-standard temperature. Good. So it's pressure altitude plus 120, and that is times your outside air temperature minus the standard temperature. So who remembers math? What do you have to calculate first on density altitude? Parentheses. Then you'll multiply that by 120, and then you add that number to your pressure altitude, okay? So let's figure out what the density altitude today at our airport, okay? So I'm gonna give you guys some numbers and you tell me what the density altitude is. All right, pressure is 29.88 inches of mercury. And the current temperature is minus 3 degrees Celsius.
What was it?
I'm sorry?
The temperature.
Temperature is minus 3 degrees Celsius. All right, and the barometric pressure is 29.88 inches of mercury. So what's the pressure altitude?
40.
Sorry?
40.
40 feet? Okay. We have the density altitude yet?
Oh, wait, no, that's wrong.
Okay.
It's
Sorry.
177.
177? Okay. What's our density altitude?
$1,377.
What did you say it was?
1377.
What's the standard temperature?
What is the standard temperature?
15 degrees Celsius.
At sea level. So where are we basically? So 15 degrees Celsius for our basically here. Because it's going to be really, really small if you correct for the 137 feet. That's not what I got.
2,994.
Sorry?
2,994.
All right. Are we all going with the pressure altitude of 177 feet? All right. Outside air temp is what? Oh, wait a minute. I did this backwards. I'm sorry. Minus. Yeah, I did. So, yeah, but it is definitely in the negatives.
Negative 3,556.
So no, I did it right. All right. Yeah, no, I did it right. Say it again.
I got negative 3,456.
All right. So the pressure altitude is 177. Plus.
I got negative 5,346.
Whoa.
Why is this different every time I type this in?
All right. What's minus 3 minus 15? Negative 18. What's negative 18 times 120? Somebody do it on the calculator.
2,160.
Add 177 to it. Oh, that's what I did wrong. It's going backwards. All right. You said 1983 before?
1983.
Got it. Minus 1983. I didn't have it. I was doing basic when I didn't throw negatives in there, so I added versus the subtracting. So what this ended up being minus 2,000 something or other, and then you just add 177 to it, and So you should have minus 2,160 when you do all the math in here, okay? So it's negative 2,160. You add 107 or 177 to that, you should come up with minus 1,983 feet.
What's
Pretty
the
good.
elevation out here again?
137. We all in agreement on this?
So that means the air is denser in this problem than,
Does this mean, with this density altitude, are we getting better performance or worse performance?
better performance.
Way better.
It's like we're below sea level.
We are, yes, absolutely. So that means that our air is
Very good.
very dense. All right? We can do another problem to show you the difference if you'd like.
Yes.
All right, I'm going to give you altitude, and I'll give you a pressure setting, okay?
It's 44 degrees in Denver right now. You always like to talk about Denver.
Yeah, it'll be something different.
Centennial.
44 Celsius.
How much?
I said 44 Celsius.
It's like 200 degrees.
Okay. Anybody got an answer?
6,385.
What do you got?
637.
Wow. For, what are we talking about right now? No.
That's
What do I got?
I got 6385 for density altitude also.
Okay. What'd you guys get for pressure altitude?
5,785.
5,785.
Okay. 5,785. What is, yeah, it's temp is 20 degrees. What's standard temp?
15.
Nope. What is our elevation? So how do we figure the temperature at that altitude?
So you have to subtract 5.8 inches.
2 degrees Celsius for every 1,000 feet. You decrease the temperature 2 degrees Celsius for every 1,000 feet. So 6,000 feet should be 3 degrees Celsius. Would be standard temperature.
So, so we apply that as a standard temperature?
You have to figure out what the standard temperature is at your altitude.
Okay.
So it should be 3 degrees Celsius roughly at this altitude. You're only, what, 15 or 115 feet from 6,000?
Sure, yeah.
We're 140 here roughly, so I mean, 0, we're doing 15 here, we're doing 3 there.
You apply that correction to the standard temperature.
Yes.
Okay. So the 3 degrees
Yes.
minus.
So 20 minus.
20 minus 3.
Yes.
Yeah. See how that makes a big difference.
Yes.
I got 7,825.
Yep. That is your density altitude. 7,825. So when you're sitting on the ground and engine's running, that is the engine performance you're getting is if you're sitting at 7,825 feet. Very, is it more or less dense?
Much less.
Much less. So this would be a typical summer in Colorado, in Denver. I've seen that once or twice. So you see what we get here, we're at almost minus 2,000 in the wintertime here. And you can do it for today in Colorado, see what you get. Do it today in Louisiana, do it anywhere, okay? But that's how you figure out the performance you're getting at the airport you're at. It's very important that you know that, because what do we need to know? Why do we care about density altitude on for our calculations? When we calculate out this stuff, why do we care about density altitude at all?
Performance.
Yeah, what
Impacts on your mixture.
where is it gonna hurt us the most right now? Well, actually right now, takeoff. You're most concerned about density altitude on takeoff. You're looking at me weird.
Nope. Just listening.
Why? Why takeoff? Why do we care about it? Why is it during takeoff that we're most concerned about density altitude?
The most power.
How long is it gonna take us to get off? And how much room do we have before we have to clear a 50-foot obstacle? Because I guarantee you, just about, unless you're flying in North Dakota, you will have an obstacle you're gonna have to clear eventually.
Hey, include Wyoming in there.
They do have terrain in Wyoming.
Yeah, I gotta teach them. Oh no.
Wyoming.
North Dakota really doesn't have much. You might hit a cow.
Of course.
So
Colorado.
this really affects your takeoff performance. It affects everything, but we're most concerned on takeoff because that's when you're most likely to hit something if you can't outclimb it. All right, a little graphic here for you. You'll see this in all the weather books and everything talking about air density. Standard temperatures in the middle, higher temperature on the right, low temperature on the left. You'll see as the temperature decreases, they all start clumping more together, more dense. That's why we've got such a great density altitude here. We have cool temperatures, we're low, we're at sea level, so all that air is packed on top of us, and all the molecules are clumped together, moving very slowly. Great for our engine, and we'll talk about how this affects us in a later slide. All right, humidity. One of the things we don't calculate out is humidity. So humidity is just the presence of water molecules. Water vapor is less dense than dry, I did that twice, than dry air. I was working on this in a hurry, sorry guys. I'm gonna clean this up before I post it, because that's gonna drive me nuts. Air density decreases as humidity increases, okay? Humidity is bad. Water vapor is the worst of the gases for us. In general, it's the worst greenhouse gas too. It just affects everything negatively as far as our performance goes, okay? Get the molecule weights, that's just general stuff I put up there for you. The big thing though is we don't calculate air density. Now, what is the interesting, how does temperature affect humidity?
Higher temperature probably reduces higher humidity.
I'm sorry?
Higher temperature probably gives you higher humidity.
Are you talking about are the,
As far as evaporation, getting it into the air.
okay, are you talking about relative humidity?
Temperature controls how much moisture the air can hold.
Yes. So the warmer the temperature is, the more moisture it can potentially hold, right? I hate relative humidity because it means nothing. It really doesn't mean anything. What matters to us is the dew point. How close are we to the air becoming saturated? Because right now, if you look, I'm pretty sure it says we're about 87% humidity out right now. But it's not going to affect us at all because we have very little moisture in there. It's too cold. As you get colder and colder, the closer to zero you get, the less moisture is in the air. You'll get to a point where there's very little moisture in the air. The air is very dry. It's just too cold to hold moisture.
Is that why it rarely like snows below 0 degrees?
Yeah, because we're below the point where we can hold moisture in the air. So a lot of the clouds you'll see, the really high altitude clouds, the cirrus, they're ice, just ice particles floating around up there. You won't get it. If you get into cirrus clouds, you're not going to gather icing on the wing. It's just good. It's just a solid already. It's going to bounce right off you. So as the temperature decreases, the air holds less moisture. The hotter we get, though, the more moisture can hold. So where's a really bad time? When's a bad time to fly an airplane?
Middle of summer, Louisiana.
After a thunderstorm.
Okay.
Absolutely. No, and in Louisiana, anywhere that's really warm, 90s and above, after a thunderstorm, because what happens in the air after a thunderstorm? Really damn near saturated. It is the most moisture it can hold, basically. In Colorado, we would fly in the mornings up to about 2 o'clock, and then we're done. It's thunderstorms hitting. We don't usually fly after thunderstorms either because our density altitude does not necessarily, just because the calculation comes down, doesn't mean that our performance is going to come down because of all the moisture. So
Then
that
why do
is-
you calculate humidity?
you don't,
And so then why don't you, if it affects?
because how can we?
Okay.
We don't have a clue. It's just one of those things you need to be aware of as a pilot. That if you're on a high density altitude day, you do all the calculations, you see that's high density altitude, and you know that the dew point spread is pretty low, you're gonna have, so what I'm talking about is your temperature, say like today, what's temperature here is what was it again, -3? So the temperature is -3. I think our dew point is like -1. It's 2 degrees, very close. I'm sorry, no, it would be -5, that'd have to be colder. So we're only at 2 degrees. We're close to saturated. So right now we have a potential fog, if that's what it is. Anywhere between, if you have 4-degree spread, you're almost saturated, you are pretty close. You have potential to accumulate fog for that to start building. So if you have a close dew point spread and high density altitude, just know that your performance is going to be even worse than what you calculated. It's just what you have to always think about. All right, density altitude, pressure altitude corrected for non-standard temperature. What does that mean? Well, we've already talked about that. So the airplane's performance is a direct function of density. What you calculate, I asked the question before, how are the charts laid out? Pressure altitude or density altitude? Well, it says pressure altitude on it, right?
But it corrects for temperature.
Corrects for temperature. So they're laid out for density altitude. They're calculating into density altitude into the mix for you. So here you go. Pressure altitude in feet. Temperatures. So it is handling density altitude for us. All right, so the engine, the propeller, and the wing produce their highest output in high density air. Low density altitude provides the best takeoff performance. Why is this the case? What are the 3 reasons that low density altitude provides the best takeoff performance? I want the 3 reasons.
It's easy to produce more lift.
What does?
When the air going over the.
So the wings are going to generate the most lift. Good, that's one.
Denser air means more oxygen, better burn.
Engines providing, it's getting hotter, more power. What's the third one?
The propeller is more to grab onto.
Generates more lift, right? That lift is generated to, or is translated into thrust. So we get more thrust, more lift, and more power. There you go. There's your 3 reasons. Low density air equals low density altitude equals high density air. High density altitude is low density air. Takeoffs. All right, density altitude, high density altitude equals poor performance. So just remember that if you got high density altitude, poor performance. As an aircraft weight. So as aircraft weight increases, required lift increases. Why? Absolutely. How do we get that new lift? More, or this is one of those instances where the surface area can change also. Because we can take off with 10 degrees of flaps in 172. Those flaps slightly extend as they come down, which increases the surface area ever so slightly. So we're increasing our attack with flaps, we're increasing and the surface area a little bit. Plus velocity. Those are the ways we increase our lift. So you have to get more lift though to equal the weight of the airplane. Typically that's going to be faster ground roll. You got to get moving faster. All right, so these are some of the other environmental factors that affect us, okay? Headwinds. Headwinds, good or bad? Good. Why? What does it do? How does it translate to us? How's it good for us? What is it about the headwind that's good for us? What does that mean? How does the ground speed translate? Somebody else. Okay. How does the ground speed translate to us? What does that mean for us? We're taking off. Why do we care about our ground speed?
Less distance to reach your airspeed.
Okay. So what you're saying is, we have our runway. There's an obstacle down here. We're going this way. We're going to be able to get higher because we're going slower. Yeah, we're getting there slower. Is our airspeed changing? No. But the rate at which we're moving towards that object is slowing. So we're able to climb and gain more altitude over that distance. Okay? Remember that. More altitude over a distance. That's going to come into play down here a little bit. What is your ground speed if you have a 10 knot headwind and your rotate is 55? So what are you rotating at? What's your ground speed at rotation? Yeah, 45 knots. It's a nice, easy conversion there. If you know what your headwind is, you know how that's going to translate to you. You're now going 45 knots versus 55 knots. You're going to get there slower. So we want that. Tailwinds push the plane along. They do not aid us in lift. I didn't put it in there. I will pull it up here in a second. We're going to look at the performance charts for takeoffs. Because that's basically, right now our discussion is going to be basically on takeoffs today. We'll be done with the rest later in the week. All right, dramatically longer takeoffs and landing rolls. That is going to also be referenced in the footnotes in the performance charts. It will give you different percentages and numbers to add into your performance calculations based on headwinds, tailwinds, and grass runways. We also have crosswinds. How do crosswinds affect our takeoff?
Depends on where the question is from.
Okay, explain.
If you've got a quarter inch from the front, you've got a shorter, you've got a, technically got a partial headwind,
Okay.
or a quarter from the tail, you've got a longer, you've got a tailwind, so.
How do we break down the winds when we're talking about crosswinds? We have components, a headwind component and a crosswind component. Does the headwind, so we have two components. There's one component that helps us, which is the headwind, and one component that does nothing for us. That's our crosswind. And then, like you said, there is a chart for that in each POH, typically. Pretty sure, The 172 has them also. So you gotta be able to calculate it out. You need to know what it is. What else does a crosswind do to us on takeoff?
It makes it harder to control.
It can. You have to use a crosswind technique when you're taking off. Does anybody know how to do that?
Keep your wing into the wind. It's dipped down slightly on the upwind side, right?
So, we have our runway. We're here, taking off that way. The winds are here. Turn into the wind. Full deflection on initial. Always full deflection. At full power. And you're going to go down the runway. As you increase velocity, ailerons become more and more effective. So, you will feel them wanting to go back to neutral. Let them, slowly. As you increase your velocity, you're going to slowly bring them back to neutral. At that point, you should be at rotate speed. Rotate, the plane will rotate and take off, and immediately what will it do?
Turn into that wind.
It's going to crab into the wind. Should you let it?
Yes.
Absolutely, because your movement is still in this direction. You're correcting for the wind. The plane will still fly down the runway like it's supposed to. Because if you turn into the wind and then you use rudder to keep the nose straight, you are now slipping the airplane, and what are you doing to your performance? You're seriously decreasing it. So let the plane crab into the wind and climb out that way. And that is a proper crosswind takeoff. Full deflection. Anytime you're dealing with winds on the when you're taxiing or initial on takeoff, it is always full deflection. Rule of thumb for winds when you're taxiing around. Dive into the wind. I'm sorry, turn into the wind. Dive away from the wind. So we're taxiing here. We're on the taxi. We're on November. We have a tailwind. Dive to the right. You have a left quartering tailwind, you're diving away from it. Why?
While you're taxiing, so you can use that tailwind to help make your taxiing turns easier.
Nope.
So the wind is not.
So it doesn't pick you up.
Yeah.
You're getting, which way is the aileron pointed? The trailing edge, is it up or down?
Down.
Down. So the air is going to more likely flow over the wing than get underneath it. That will help keep that wing down. And the elevator, is that trailing edge up or down as you're diving away? Down. So again, the air is going to be over top of it versus underneath it, less likely to pick you up. Okay? Very important that you know how to do crosswind taxiing in a tailwheel. It's important for us, but the tailwheel is way more susceptible to ground loops with wind. So it affects us on the taxi and the takeoff. Runway gradient. How's that going to affect us?
Incline decreases performance, decline increases performance.
Good. What about the surface? Name some surfaces that are the worst to land to take off on for performance. I'm sorry?
Grass.
Okay, grass is not great.
Tundra,
Grass.
uneven.
Dry
Kinda. Sand is not great.
Mud.
Mud's not great at all. Slush. Slush is the worst. Slush. Mud and slush and wet sand are really, well, wet sand's pretty hard to pack. Dry sand would be pretty bad too, I would imagine. But slush is horrible. So anything that the wheel can sink into is bad. Wet grass is really bad. Dry grass is pretty bad too. So anything that's just, usually when the ground is wet with grass, it's spongy and you sink into it. And we have a technique for that. And we'll talk about that in a second. All right, what about the use of flaps?
What about them?
Do they aid? Do they not aid? What do they do for us? What does flaps help us out with?
Going slower.
Can, yeah.
increasing lift.
Does increase lift. helps get the weight off the wheels sooner. And that's the big thing. When we're talking about the soft field takeoffs, the technique is full back pressure. You want to keep the weight off the nose. Why weight off the nose?
So you're keeping weight off the front tires.
Why?
So they're not digging in and.
Yeah, because it's 1 point, and it will dig in because the weight is going to be more forward on the nose while we're taxiing around, unless you have the back pressure and keep the weight off the nose.
It's the same idea in a tail dragger? Or
I couldn't honestly tell you because I don't fly tailless. Theirs is a little different.
We're already angled up.
I would assume that it doesn't make a big difference on them because they want to get the weight off the tail as quick as possible to get off the ground. So I'm not 100% sure. I've never flown a tail wheel before, so I can't tell you for sure. But when I do, I will let you know. If you fly one before I do, let me know.
I've ridden in one, but I didn't know what was going on.
I've been in them too. I've just never flown. And I never took off on one on a dirt or a soft field, so I don't. The flaps, yeah, we use flaps for shorts and softs. They get us, the point is to get rotated and up. With the soft field, we're getting into ground effect to increase our airspeed and then climb out. With a short field, we're getting up and we're climbing out at a very low airspeed, so we need the angle, the added angle of attack.
Why not use them all the time?
Because you don't really need them. You get better climb performance without them. You can gain better speeds because it's to help get us off in a shorter distance. You can use them if you want to. Once you get to after the cross country, once you get into the cross country phase of training, you will be doing nothing but shorts and softs for the most part. I mean, on landings, the FAA recommends you land with full flaps. So you want to land at the slowest speed. Do you have to? No. We routinely practice zero flap landings. And they're a little odd for students because the attitude that you have coming in, the sight picture is way different. You are really nose high, and you're almost at idle the whole time. Otherwise, you're too fast. So, flaps are good for getting off the runway faster. So, if you're doing short field technique all the time, you're using flaps all the time. Airliners have to use them because they need that lift to get off sooner. Get up and go. Those are very heavy. So that would be back to that question before about that one. As weight increases required lift increase, flaps. That's another way, like I said in the previous, we talked about angle of attack, velocity, and surface area were all the three areas that we affect for a takeoff with greater weight. Airliners are a great example. They always take off with a certain degree of flaps. Not full, but a certain level.
And they have a higher range of flaps also.
Oh yeah, right. And every airplane is different. The 182s have, what was it, 10, 25, and 40 degrees of flaps. We have 10, 20, 30 on ours. I've flown older Cessnas that have 10, 20, 30, 40 degrees. They stopped making those on Cessnas because people were landing at airports that they couldn't get out of. The landing distance is so short, they could get in there, but they couldn't take off because they didn't have enough performance to get out of it.
Get rid of the option.
So they stopped doing that. Because with 40 degrees of flaps on 172, you can make it seriously short. It was stupid. It's like watching the SOL competitions.
Yeah.
I've done it where I was coming in at 45 knots and we just were doing this.
It is STC to change it so you can go back to 40.
Is it?
Yeah, that's STC.
I don't mind it because I would never land at a place where I would look at my performance charts and see, I can't take off that airport even though I can land there. But
some people didn't.
it is really fun. Like, I wish this university would do landing, short field landing competitions for the instructors because I think it would be really eye-opening for some people. It would be fun, and I would partake. No, here. We have a great 50-foot obstacle right there.
Trees.
Yeah, but the planes we have are not capable of doing what theirs goes with. I'm saying we select one airplane that everyone flies so that it is uniform. And we all compete against each other, see who can get off. Joe asked, I almost had Juliet on an icy runway. which if anybody knows, Juliet is the second taxiway right there. I came in seriously slow. And right on the threshold. Didn't you think I was gonna hit the grass?
No, that was someone else then, not me.
So, yeah, that's back to the flaps. The flaps, that's what they're for, is to help assist with the higher weights and get off the runway faster. All right. Climb performance. So we're going to talk, I'm going to pull up some of the diagrams in the POH here in a second. We're going to talk about the different things. All right. Maximum performance climb. What would be a maximum performance climb? No, we already, I talked about it. It's not anything like that. It's the type of climb, the type of takeoff we're doing. What would be the most maximum performance type climb that we will do in our airplanes, in general aviation airplanes? So we're not F-22s, we're not going vertical. Sorry, guys. I'm sorry?
Slow, high, go back.
What kind of takeoff is that? A short field technique takeoff. So short field takeoffs are the maximum performance climbs. On our airplanes, we rotate at 50 knots, climb out at 56 until you hit your 50, until you are above the 50-foot obstacle. Rotate to 62 knots, which is best. We'll talk about that in a second. So 62, continue to climb out until we hit a given altitude that we're comfortable with. I usually go about 400 feet. Flaps up, accelerate to 74 knots, and continue your climb at that rate until you get to the altitude you're looking for.
62 max flap speed, which
Nope.
have these.
And this is with 10 degrees of flaps. And all of the short field technique talks about how to set the airplane up before you go. The actual way that we teach the technique is in, we have a manual, what's it called? The guide that we have that goes with the TC.
Maneuver description guide.
Yeah, the maneuvers description guide is a UA product. That's what we have as instructions. We have to teach the maneuvers by that. And also piggybacks, it is drawn heavily from the airplane flying handbook. Everything has to be in accordance with the airplane flying handbook. It's just specific to the airplanes we fly here. And that's the technique. What's outlined in the maneuvers description guide is how we as instructors teach the maneuver, and you guys as students can study that guide to know how to properly execute the maneuvers here at UA. And they're pretty much correct everywhere. That's how I usually teach them anyways, because it's per the airplane flying handbook. So that would be a short field takeoff. What is the best rate of climb?
62 knots.
No. It's another name. What's a B speed associated with best rate of climb? Why? Where did you find that? There's a different place I'd rather you were looking. Yeah, where in the POH? Nope. I'm going to amend the syllabus. We're going to have an additional final where it's going to be all stuff out of the POH. The airplane flying handbook and the airplane pilot handbook.
Someone ticked them off.
It's in the normal procedure section. It's because it's VY and the best rate of climb are normal procedures. That's what we typically climb out is, what's the speed? What is best rate of climb? I said two numbers on the climb out. Pick one. 74 knots. It's your best rate of climb. Okay? So what is best angle of climb? What's the V speed?
VX.
VX. Okay? I said earlier we were talking about the climb out with the headwind. And I made a comment that, hey, we will discuss this later. Does anybody remember what I was talking about?
62 knots.
Well, I was talking about the headwind and how it did something for us. We gained more altitude over a given distance. That is VX. Your best angle of climb is going to give you the most altitude over a given distance. The best rate of climb is going to give you the most altitude over a given time. That's the difference. So if you think of angle, altitude, and distance, you have a right angle, that is best angle, Vx. Okay? I just remember X, math, angles. That's how I always remember best angle versus and Vx. And Vy is usually what we always climb out at, and that is 74 knots. So who's actually looked at that portion? Does anybody know where in normal, the normal section I'm talking about in POH?
Customer section.
Section 4?
Yeah, section 4. You guys, are you on it right now? What is unique? That is not normal procedures.
It has all these.
Yes, you're in general. Look up at the top, it says section 1, general, right?
Yeah.
Go to section 4, normal procedures. I want to know what is unique about that portion when we're talking about the best, because it doesn't label it as Vx and Vy. General talks about Vx and Vy and defines them. The normal section talks about the speeds themselves, okay? Let's see if my memory is any good. You got it?
You don't like the chart.
Not chart.
75% power.
It is a list of information on, so the first page of the general should, or of normal procedures should give you the different pages. Second or third page should give you some information about speeds and other things like that. Okay? Best angle of climb at sea level, what's the speed?
For climb speed?
Yeah, best angle of climb. See what you're looking at.
Oh, it's like the 70, 80.
Nope.
62. On page 82 of it.
What is best angle of climb at sea level?
62,
What is best angle of climb at 10,000?
67.
Oh, so close. Okay. What about best rate at sea level
74,
and best rate at 10,000?
72.
Weird, huh? So your speeds change with altitude. What's happening to Vx as you go up, as altitude increases?
It increases.
And what happens to Vy as you increase altitude? Those speeds will meet. Does anybody know what you've reached when those speeds are the same? What's the surface ceiling of this airplane? 14,000 feet? Where would you find that?
Anyways,
Where in the POH? So when I ask you
the Cessna Bible.
a little more info than just the POH. There's a lot of information in the POH.
It's 14,000 feet.
Where did you find that?
Found it in the introduction.
There you go.
Performance specification.
At 14,000 feet, does anybody know what you're able to maintain at 14,000 feet? A 100 foot per minute climb rate. And that airspeed is where those two numbers meet. That altitude, your surface ceiling Because where those two numbers meet, here is only one speed, you're gonna be able to maintain 100 foot per minute climb rate momentarily before it starts degrading because you're gonna pass through 14,000 feet.
You had a Cessna at that altitude, 14,000?
I have not. I've had one at 12,500. I think I've gotten up to 30. That's 12,500. So, all right. So best rate and best angle. When would we use the best angle of climb? Give me a situation, not a short field or anything like that, but the situation.
You have to clear a big building or mountain.
Not a short field,
Obstacle.
not necessarily an obstacle. I would not try to clear a mountain like that. Raise your hand if you have the chart supplement. Open that up for me. Everything we're talking about right now has a practical application to your flight training. Stuff you're going to have to know how to do. And the situations you need it. Let me borrow that real quick, okay? I'm going to walk around. I'm going to show everybody something. No, that's salmon book. Okay? In the salmon book, bunch of airports in here. This is the chart supplement for Alaska. All the airports in Alaska that have been charted are in here, okay? And you can flip through them and you'll see them. We are near the front. That's right over there. There's Merrill Field. We are on page 43. We're near the front because we fall under Anchorage. So we'll be under the Anchorage portion of it, okay? Now, reading through the different, if you go through the beginning of it, it's going to tell you there's going to be a section back here where they talk about the different procedures, okay? If you want to do one of the departures out of Merrill, here's one we do. You want to read about this one in this book, okay? I'm going to show it to everyone. What's it called? Inlet departure. This is what you will be doing every time you depart out of Merrill. Go across the water to the practice area. The description of this maneuver, yes, see if back there, okay? The description of this maneuver is on this page. How to execute this departure procedure. Okay, so you're going to want to go to page 386.
So it's the same version.
Inlet departure procedure, okay?
Where does one apply that book?
Northern Lights.
Avionics.
Yep, Northern Lights avionics.
Or the internet.
Or the internet. Okay? This is one of several departures. On the next page, on 387, you have the shoreline departure, which used to be the UAA departure. City High departure, Chester Creek departure, Campbell departure. I must have missed it. I did. And then on page 385 is the one where you might want to do this maneuver. It's called the Ship Creek departure, okay? If you take off of runway 25 or 34, 25 is the one where you're taking off to the west, 34 is taking off to the north. If you take off on those runways and do the Ship Creek departure, you were supposed to take off and immediately turn to the mouth of Ship Creek. Well, we have an issue here. What is just to the north of us?
Elmo.
Elmendorf, yeah. Guess what they have? Airplanes that like to land on a runway they have there. Guess where the approach end of that runway is? Right through the inlet that we are going to be crossing over. So, what's one of the things we want to try to do as pilots? Avoid, well, one of the best ways to not die is to avoid other airplanes, okay? Problem with C-17s, C-130s, C-5s, F-22s. Problem with these military aircraft is they're kind of camouflaged. I've seen C5s in here a lot.
Yeah.
So we have
Land and
a
break.
regulation that we have to follow. Part 93. Homework assignment, look up part 93 and read about it. Part 93. So 14 CFR, part 93. Okay? Go remind me to ask about it on Thursday. You know I'm going to forget.
This is my last one.
Oh, it's not.
This is-
We're going to keep
I have
coming.
a 5. Oh, okay. Last one I'm filming.
Oh.
Okay.
All right. So we have to maintain a block. There's a block of altitude that we have to avoid as we cross the inlet. We have to be from 600 to 2,000 feet. We cannot be in that area. So to cross the inlet, we need to be below 600 feet, which when you're crossing the water in a single engine without floats, not a great idea. There's no escape route if you lose an engine at that point. You cannot glide back. The inlet's too wide. So we're not going to do that. And that is, you are not allowed in UA airplanes to cross the inlet anything less than glide distance. Okay? So that means we're going to have to cross above 2,000. Well, our block is 22 to 2,500 feet. That is our block of airspace from the edge of from Westchester Lagoon over to Ship Creek across to Point Mackenzie and Point No Name. That is our corridor and our elevation block, 22 to 25. Well, if you do a Ship Creek departure, you are turning at the mouth of Ship Creek and climbing. You need to get your altitude before you reach mid-channel, because at that point you are at mid-channel, you're abeam the approach end of their runway. So that is where you have to be at your altitudes, by mid-channel. So if you are looking, as we're departing out, if you're looking over your right wing and you are looking right down their runway, and you are not at your altitude above 2,200 feet,
You are
you have
wrong.
deviated part 93 unless you've been given an altitude deviation, which is possible if they're not flying. But if they're flying, you better be above 2,200. Now, if you're taking off in those two directions where you don't have a lot of room to climb, you might consider the best angle of climb. So let's think back to headwinds. You typically take off with the headwind. Now, I'll tell you, here at Merrill, we do a lot of flying with a tailwind. They love 2.5. They don't like to change runway 2.5 unless they have to. The winds start getting upwards around 8 to 10 knots, then they'll ask you if you want to change. If they're above 10, they will change. Typically, is what I've seen. I don't know their policy on it. I've never asked ATC. I don't really care too much. We have 4,000 foot runway. We've done more than enough. But if we're taking off with the headwind, so you have 10 knot headwind, climbing out at 62 knots, we have a 52 knot ground speed now. If you maintain that all the way up, it gives you more time to get that altitude. Because you have that distance now is going to, you have the distance is fixed. So it's going to take you longer to traverse that space, gaining more altitude as you do it. I have done plenty of takeoffs here and had mid-channel. Actually, I've had to throttle back and level off because I was going to hit 2,500 feet. Without a deviation, no need of a deviation. And I did a regular takeoff, 0 flaps, I just pitched for 62 on the climb out. We can make the altitude, especially right now, because why? Why? Density, yeah, the low density altitude we have right now. We have a ton of performance. So you can make it. Now, without it, you would do the inlet departure. And that, you want to get in here and review these, learn these. I typically have to bust this out and look at the city high because we rarely do that one. That one is you take off, basically fly down over UAA, circle and come back, and you'll have your altitude by then. Because you're basically climbing the whole time. It's one way to get it. The inlet departure has you take off 2.5, you climb out over Ingra, you turn crosswind, which for us right now is the left wind. You're turning left crosswind, level off, continue to climb on the crosswind, get to the downwind again as you're continuing to climb. Once you have 1,300 feet, you can then turn northbound and circle and line up with 9th Avenue Park and continue to climb up to 22 to 2,500 feet. And once you hit the shoreline, you're typically given your altitude, your frequency change to approach, and then you shoot across towards sleeper strip, which is dead center between Point McKenzie and Point O'Hare. That's the inlet departure. You will do that almost every single time. Thank you, sir. Appreciate that. The Part 93 information is also in the Salmon book. All right. So that basically takes care of the best angle of climb. When would you want to use the best rate of climb?
Most of the time.
Pretty much every other time. Because the best angle or best rate is going to be your normal takeoff for the most part. You're not really concerned about anything. You're just taking off and you're just getting the performance. When you do an inlet departure, you're doing VY, best rate. Because you're going to get the altitude. You're not really worried about it. You just want to get there faster. All right. What other kind of climb do you think there might be? It's not in the POH for us, but it's another thing you can do. And it's just kind of a bonus question to see who has any, who might know.
What was the question?
What other kind of climb is there that you can do besides the max performance, the best rate, and the best angle? A cruise climb. The airplane flying handbook talks about it. So think about the VX and the VYs, especially the VX. With your best angle of climb, what are you doing with that airplane?
Burn the whole lot of gas.
Yeah, but let's talk about the positioning of the airplane in climb. Yeah, nose high. Very difficult to see in front of you. That cowl is in the way. And to somewhat of an extent, your best angle of, or best rate of climb is no different. You're still, the cowl is kind of in the way. Now, if you're in a high density altitude area, or say just a hot environment, you're doing a lot of work on that engine on those two climbs. So what can you do to help cool the engine? Lower the nose, increase the airspeed. You're still climbing. We could do a cruise climb at 90 knots. You're still climbing. Do we care about how quickly we get to altitude? No, not really. If you're on a cross country, you don't care. You're going to get there eventually. If you're you're flying from here to Talkeetna, you've got about 45 minutes worth of flying. If you're climbing out at 85, 90 knots, you'll get your altitude. No problem. You have better visibility and better engine cooling. So a cruise climb is another form of climb that you can do. I wouldn't recommend that in the terminal area. Once you take off, you want to climb until you get to a certain altitude. Usually when I flew twins, when I was doing my commercial training, 500 feet AGL above the ground is when we would level off the cruise climb. And it just helps keep the engine cooler and better visibility. So that would be another option, because you are really working the engine pretty hard on this. Is it a big deal for us right now? Not really. All right. So I was going to show some charts, but I don't know that we really need to. Do you guys feel like you need to see charts right now? Or are you feeling all right? Any questions so far on what we talked about tonight? We talked a little bit about the atmosphere itself and how that affects performance. Obviously, I hope you guys understand how important density altitude is. It does not affect us negatively here, so you don't really have to worry about it, but you will not always be flying here. It affects airliners for a different reason. In Phoenix, it's common for them to ground even the airliners at Sky Harbor. Has anybody ever heard of them grounding airliners at Sky Harbor? Yeah. Why? What did they exceed?
Probably takeoff temperature.
Takeoff higher.
Nope. They exceeded the temperatures that were in their manuals. They had no calculations. That was the only reason. Not that they can't do it, they just didn't have any calculations. It's outside of their normal operating, the parameters that they have calculated. So without it, if you don't follow the POH and you're operating outside of what the manufacturer, the information the manufacturer gave you, what do you become?
Test pilot.
A test pilot. And you cannot act as a test pilot.
With hundreds of lives on the line.
Unless you are hired by somebody, you cannot act as a test pilot. Not with paying passengers. Not with
Usually just your
paying
soul.
passengers.
There's
Rebellion.
a chain relay for that.
Only you in the plane.
So
Right? So density altitude is really, really, really important. And there's another thing that really, there's two things that I will harp on constantly. Density altitude and leaning. Leaning. Very, very important, okay? If you ever have an instructor who tells you, well, we're at sea level, we don't need to lean for taxi or anything like that, slap him and send him to me. If you didn't slap him hard enough, I will. You will foul spark plugs. It will affect your performance over time. We had an airplane go down for maintenance 2 days ago down at Angel because the spark plugs were completely foul. They could be used. They had to be chucked, and they had to put new spark plugs in. Because of leaning. So you're putting too much fuel in there, you're not burning it. So lean. And once you get to a high density altitude and a high altitude at airport, it's very important you know how to lean. Because if you're running too rich, you are robbing yourself of power. When you're already operating at 70, 60, 70%, maybe 80% if it's in the wintertime, of what you normally get.
But in low density altitudes, you don't want to lean.
Yes. Not for takeoff and not for landing. And in the pattern, no. But for taxiing and in cruise, you lean. If you want to know that you leaned properly for taxi, get it down to run up. Well, goose it on taxi, and if the engine starts sputtering, if you get it up to around 2,000 RPMs and the engine starts sputtering, you'll lean it properly. Because the taxi lean should be way more lean than your run-up power settings. So that's how I knew that we had leaned it properly in Colorado when we taxied, because when you get to the run-up area, I would always go rich and then throttle up, and then you lean for takeoff. Above 3,000 feet, MSL, you have to, it is recommended that you lean. Because anything above that, air density. If you go higher, less air molecules. Okay? So lean, and and density altitude is very, very, very important. So you guys now know how to calculate density altitude. See how it's done. So play with that. You know, just when you're going on flights, find out what your density altitude is for that day, and get an idea of what it was like in the summertime versus wintertime, and see how your performance changes while you're flying. It's amazing. The climb rates I'm seeing right now are almost 1,000 feet per minute. It's insane. In the summertime, it's like 600, 700, which is pretty good. Colorado, I stayed about 500. 400 in the summertime. In the same airplanes. So.
So is Alaska all over just kind of better for performance in general, or?
Yeah, because we don't have a
weather
ton of that.
conditions usually?
Well, we have cool air, not the most humid of air. And so the cool temperatures, the humidity, the lack of humidity, and we have low altitudes pretty much everywhere. I mean, the further you go into the interior, it goes up, but other than Denali and the mountain ranges, it's low altitude. So it definitely helps with the flying. So I highly recommend, though, if you guys ever go on vacation down south somewhere, rent a plane and fly, see what the difference is. It's pretty massive. So then get a different viewpoint from the way that the instructors teach the operation of the aircraft. So it's always good to get the different perspective from different people, different instructors. The moral, like this, the technical information should always be the same, but there is always wiggle room in there. Like I said, with the flap settings, I use 20 degrees of flaps, and I like to use final flaps in my turns because it offsets the loss of vertical component of lift, and I don't have to add the back pressure. I stay stabilized all the time. That's my technique. It's not required of my students. They can do it whenever they feel like it, as long as it's happening and they know how to correct for it. Okay. Your approach speeds. POH recommends 60 to 70 knots on your approach speed. I will approach. I use 60 on final, but I slow that plane down significantly the closer I get to the runway. I want to land slow. As long as you're doing what the book says and what the FAA says, you're okay. And if anybody tells you to do something that's outside of that, they're wrong.
You are wrong.
All right, no questions? You guys look like you're ready to get out of here. Everybody sign in?
Sign in or as if you were not here.